We'll get started. So yesterday we discussed about prism, right? So with that, by the way, those who are online are able to hear me?
Yes, sir.
Okay. So with that, we have come to the end of refraction at planar surfaces. Now we need to start with the concept of refraction at spherical surfaces. Right? See, there is a boundary which is curved instead of being planar, right? Then, with respect to the curvature, we take the point P here, okay? And let's say the center of curvature is lying somewhere over here. Now, if I take a point object here, what am I considering? I'm considering a point object and not an extended object. This is a point that you need to make a note of. Okay. So let's say this is rarer medium and this is denser medium. And let's say a ray is incident from the rarer to the denser medium. I'll take the point here. Now, at the point of incidence, if you draw a normal, then this becomes the angle of incidence, right? So when the ray travels in this path, right, when the ray is traveling from rarer to denser medium, what happens? It starts bending towards the normal. So when it starts bending towards the normal, this is going to be one of the refracted rays. I'll say refracted ray 1. Okay. Then the other refracted ray that I can consider is going to be along the principal axis itself. So when the angle of incidence is going to be 0, the angle of refraction is also 0. As a result of which, I can say that this is going to be the second refracted ray. So we are able to clearly understand that the first refracted ray and the second refracted ray are definitely not going to meet in real time. So you extend it backwards, right? You extend it backwards and you will be able to observe that the image is formed here. Is the point clear? Okay. Now, so the second point to be noted is this is the angle of refraction. Is it clear? Now see, if I take this point to be M, even before we proceed, there are certain assumptions that we need to know. So the assumptions that are taken into consideration are: first, rays are paraxial in nature, in the sense they are very close to the principal axis. Second, curvature of boundary is very small, such that we can say that this PM is there, right? The curvature PM, such that the curvature PM is approximately a straight line. It's approximately a straight line. So the important points to be underlined here are rays are paraxial in nature and curvature is very small. Now, having these 2 points in mind, what we can do is, if this angle is R, okay. Now, if I zoom and see, this angle will also be R. Is that right? Because they are vertically opposite angles. So how much will be the remaining angle? It is going to be I minus R. So what I can do now is, I will apply Snell's law at point M. So when I apply Snell's law at point M, I can say mu1 into sin I is equal to mu2 into sin R. Since rays are paraxial in nature, what will happen? All angles considered would be small, in the sense sin I can be approximated to tan I can be approximated to Ix. Or to put it in simple terms, sin is approximated to tan is approximated to the angle itself. Is that clear? Right. Now the next question is C. If I take this angle to be alpha, if I take this angle to be beta, and if I take the third angle to be theta, then how many triangles are you able to find? I am able to observe the triangle OMI. So I am able to observe the triangle OMI, where this angle is alpha, this angle is beta, this angle is how much? Yes. This angle is I minus R. Similarly, if I take the other triangle MI or IMC, this angle is theta, this angle is beta, and this angle is R. So from this triangle, what can I conclude? Beta is equal to alpha plus I minus R. Exterior angle is equal to sum of opposite interior angles. Similarly, theta will be equal to beta plus R. Is that right? So from this, if I rearrange it, I get I is equal to okay. I can find another triangle also. So what I can do is I can find the triangle OMC. If I take OMC, this angle will be I. This angle is alpha. This angle is theta. So what can I say from this? Theta will be equal to alpha plus I, which implies I is equal to theta minus alpha. Similarly, R will be equal to theta minus beta. Let this be 2. Let this be 3. Using 2 and 3 in 1, I'll get mu1 into I is what? Theta minus alpha is equal to mu2 into theta minus theta. Can I say this? Let me call this as equation number 4. First copy it till this step. From wherever you need to copy, do it. Okay? I didn't get it. Are we supposed to know? Yes, you have. For this derivation, you have to. And this derivation is important as well. It is simple, no? It is logically you find 3 triangles out of which you need to select 2. It's up to you because there's one such diagram. Or if you interchange the medium, denser and rarer, that will give you another scenario. There are 8 possibilities, I think. So mu1 into theta minus alpha is equal to mu2 into theta minus beta. Is it clear? Then, yeah, please make it. Now comes the next point, that is, if I look at the different kinds of triangles that are possible with respect to M, so this is M, this is P, you have the principal axis here, right? From M, if you join to O, you get alpha here. If you join it to I, you get beta here. If you join it to C, you will get theta here, right? I told you that PM is approximately a straight line. So it is approximately a straight line. In the sense, what I can do is, so this angle, sorry, this distance will be U. This distance will be V, and this distance will be R. Okay. So if I take the triangle MPO, where this is alpha, this is U. So what is tan alpha? PM divided by U. But I told you all the angles are small. This can be approximated to alpha itself. Similarly, if I have MI or MPI, then this will be beta. Then what is tan beta? PM by B, which is approximated to beta. Similarly, I have MPC, where this is theta, this is R. So tan theta is equal to PM divided by R. This is approximated to theta. Now I will take all these values and call it as 5. Okay. So I will use 5 in 4. When I do this, I'll get mu1 into theta minus alpha. So theta is how much? Theta is PM by R, but observe. PM by R with a negative sign because I need to use sign convention. Minus, what is alpha? PM by is equal to u2 into same PM by minus U minus beta is PM by minus U. Theta minus beta. Or theta is R. Is it right? So what will get cancelled? PM is gone. So minus mu1 divided by R plus mu1 divided by U is equal to minus mu2 divided by R plus mu2 divided by V. So mu2 by R will come this side, mu1 will go to the other side. Mu2 by R minus mu1 by R is equal to mu2 by V minus mu1 by U, which implies mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. And this is the formula for, this is not Lenz's formula. This is the formula for refraction at spherical surfaces. Is it clear? Okay. So an important note here is sign convention should be applied during derivation and while solving problems as well. So having this in mind, what we can do is observe. I'm giving you the same kind of a spherical surface. Okay. If this point is P, the only thing I'm going to swap here is this is denser and this is rarer, where this is mu1 and this is mu2. A point object is placed here and the center of curvature is still here. Now I want you to derive the same refraction at spherical surface for this scenario. 5 minutes time, do it. First draw the diagram and then proceed. Diagram itself will change. You can try and see. It will not bend towards, no. You got there towards because it bent between the normal and the actual path. But this time it will be away from both. Try and see. Try the diagram and see. And you yourself compare and see. Those who are online, I want you to solve this. If you want, you do one thing. Do a small experiment and see. Don't use sign convention and see. Use sign convention and see what values you are getting. mu2 by v minus mu1 by mu2 minus mu1 divided by r. Same. You should get the same. Did you get it? Did you see that the diagrams are different? If you had not used sign convention, what would have happened? You understood why you need to apply sign convention? For you to get a generalized formula, or else you need to remember the expression for each scenario. If I'm not wrong, this is the diagram you would have drawn. And this is the actual path, right? And you would have drawn this to come and hit here. Is that right? What if the ray got bent like this? It can. It is still away from normal. In this scenario, it would have formed a virtual image. So, with respect to a ray moving from denser to rarer, there are two scenarios possible. Depending on what is the amount of bend or deviation the refracted ray is taking, it can either form a real image or a virtual image. Real image would have been formed when it is bending more. Virtual would have been formed when it is bending slightly less. Means if it is very much closer to the actual path, it will form a virtual image. But even for this scenario, if you take the angles and the proceed, you should get the same answer provided you apply sign convention. Or else you will get different values. So the expression is mu2 by v minus mu1 by u is equal to mu2 minus mu1 divided by r. Is that clear? So this is how it works. Right. Now, having said this, we will go to the next formula or next derivation, which is called as lens maker's formula. Okay. So for this, observe. Let's say you have a lens. Okay. So here you have a convex lens. So in front of a convex lens, what is happening is you are placing a point object at a distance u from the optical center. Right. Now, if you consider one of the rays to be in this format, right, then what is going to happen is, if I assume that this is the rarer medium and the lens is taken to be denser, okay, this is one such scenario. If I take it to be in this format, then what can I say about the ray which is traveling from one medium to another? So to put it in simple terms, this incident ray is undergoing how many refractions? It is undergoing 2 refractions even before it formed the final location of the image. So in the first refraction, what I can say is, there is a scenario where an image is formed. Okay, an image is formed in the glass medium or inside the lens medium itself, right? Where this image will start acting as the object for the second refracting surface, and then the final image is formed. Okay, means if I break this lens into 2 parts, in the first refracting surface, what I can do is, if I take this to be the incident ray, right? If this is the angle of incidence, let me call it as I1. So at the point of incidence, we have a normal, and that normal will pass through the center of curvature of the first refracting surface. And this is the actual path. So ray travels from rarer to denser, so it starts bending towards the normal. Again, I don't know whether this is the amount of bend it is going to take. This is also assumption only. So assuming it has taken this level of bend, then this angle will be R1. Okay. And I'll consider another ray incident along the principal axis, which will travel without any deviation. And I'm saying the image is formed here. Now this I1 will start acting as an object for the second refracting surface in such a way that for the second refracting surface, which is like this, right? Even before that, if I take a part of this ray that has got bent, so this part is there, no? So this part is this. Did you understand? I took a small line segment, and that line segment is the amount of portion that is present inside the glass medium itself. So what I'm trying to say is, had the second boundary not existed, then the image would have formed at I1. But it is existing, right? So this is only a virtual kind of image which is acting as the object for the second lens. So had this not been there, it would have traveled in this path. But since it is there, it travels from denser to rarer. So it starts bending away from the normal. So this is the normal, and it starts bending away from the normal so that the final image is located at point I. Then this distance will be V, and this distance will be V1. Okay. This distance will be U, and this distance will be V1. Means the distance between the optical center to I1 is considered to be V, and the distance from the optical center to O is considered to be U. So I'll give you a minute time. Observe this. If there is any doubt, let me know. No need to remember like that. No. Irrespective of whether the ray goes from denser to rarer or rarer to denser, or how much ever bend has taken place, refraction at spherical surface has only one formula. What is it? Mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. You can use it, but that's what I'm saying. You need not worry about whether denser to rarer or rarer to denser. Whatever is the scenario, as long as the refracting boundary is curved in nature, you can apply that formula. Because you have already derived it using sign convention. So while you're applying the formula, you need to use sign convention again so that you get the answer for that specific condition. But here, observe what I'm going to do is, if you observe what I'm going to do, concentrate for, sorry, for first refracting surface, when I apply the refraction at spherical surface, I'll get this is mu1, this is mu2. I will write mu2 divided by v1 minus mu1 divided by u is equal to mu2 minus mu1 divided by r1. If you observe an important point, I didn't do something. I didn't apply sign convention for u. Can you tell me the reason? This is a scenario where I didn't apply it. Because this is only a situation which is what we are assuming. This is not the exact location of how the images are going to be formed. Okay, so whenever you are not sure of this is the right scenario or this is the right situation, you should not apply sign convention. So this is one such formula where we don't apply sign convention at all. So for second refracting surface, mu1 is the place where the final image is formed. So mu2 will be replaced with mu1 divided by, where is the final image formed? At a distance v, minus mu2 is the area where the image is, where the object is there. So mu2 divided by v1 is equal to, what should I write? Yes, I should write it as mu1 minus mu2 divided by r2. Now what I can do is I can take the first equation and second equation and add them, so that I will have mu1 by v minus mu1 by u is equal to mu2 minus mu1 into 1 by r1 minus 1 by r2. Okay. So what will I have? Mu1 into 1 by v minus 1 by u is equal to mu2 minus mu1 into 1 by r1 minus 1 by r2. First copy it to this step. Write it down. So in your notes, you can write it down referring to the diagram in page 326. Is it clear? Shall I proceed? Done. Done. Now listen to this. So when I have mu1 into 1 by v minus 1 by u is what? 1 by f, that is according to Lenz's formula, is equal to mu2 minus mu1 into 1 by r1 minus 1 by r2. Okay, let me write this again. So what did we have? Mu1 into 1 by v minus 1 by u is equal to mu2 minus mu1 into 1 by r1 minus 1 by r2. So 1 by v minus 1 by u is 1 by f is equal to, take the mu1 to the other side. When you do that, you get mu2 by v, sorry, mu2 by mu1 minus 1 into 1 by r1 minus 1 by r2. Is that clear? And this formula is what we call it as Lenz maker's formula. So why we call this as Lenz maker's formula is because, you know what is 1 by f, right? It is called power of Lenz. So generally when you go for an eye checkup or something, what do they check? They check the power, right? So when you try to define or design a lens, right? There are certain factors that you take into consideration. What is that? The refractive index of the material that is used, the refractive index of outside medium, and the radii of curvature. All these things are taken into consideration for you to even define or design a lens. So that's why it's called as lens maker's formula, where mu2 is the refractive index of material medium. And mu1 is what? It is the refractive index of outside medium. R1 is obviously the radius of curvature of the first boundary, and R2 is the radius of curvature of the second boundary. Am I clear with this? Right? Now, having said this, there are some important points that we need to understand with respect to lens maker's formula. There are some important notes that we need to take. One is, if lenses if lens of refractive index mu2 is immersed in a medium of refractive index mu1. Okay, if lens of refractive index mu2 is immersed in a medium of refractive index mu1, where mu1 is greater than mu2, then the question is, what will happen to the nature of lens? What will happen to the nature of lens? Check and see. So 1 by f is equal to, it is mu2 by mu1 minus 1 into 1 by r1 minus 1 by r2. Right? So 1 by f dash will be equal to how much? mu2 by mu1 minus 1 into 1 by r1 minus 1 by r2. So initially, let's say it is in air medium, then it would have been mu2 by 1 minus 1. Now what will happen to f dash? mu2 by mu1 is less than 1. So when it is less than 1, what can I say about f dash? It will become negative. Means, can I say that nature of lens will change? Are you able to understand what I'm trying to say? Means, if you take a convex lens and immerse it into a medium. So what am I saying is, if you take a convex lens and immerse it into a medium of greater refractive index, it starts behaving like a concave lens and vice versa. Is that clear? Okay. Second, if you have a lens like this, and if it is cut vertically in this format, then what will happen? You will have a plano-convex lens and you will have an other plano-convex lens. Right? What will happen to them? So what will happen to the new focal length? So f dash and f dash will change. So focal length changes. Are you accepting this? Whereas if the same lens is cut horizontally, then what it, focal length remains the same. Why? So why is it changing in the previous case and why is it not changing here? Because in the previous case, R will change. Because one is curved and the other becomes a planar surface. Whereas in the third scenario, both are having the same radius of curvature. So it is going to have the same focal length. Okay. Next is, so this is all about the lens maker's formula. Now you have a concept called as power of lens. When you take a convex lens like this, okay, when you take a convex lens in this format, if you take a ray parallel to the principal axis, what will happen to it? It starts bending and the final image is formed at the focus. So from the optical center, if I take this distance to be small f, then you can observe that the ray which is considered, let's say at a distance of 1 unit from the center. Okay. Then it is observed to have a deviation of delta. Is that right? So if this is delta, how much is this? This is also delta because it is alternate interior angle, right? So power of lens is defined like this. Tangent of the deviation suffered by the ray which is incident at a unit distance from the optical center. So what can I write tan delta S from the right angle triangle? 1 by F, and this is what is called as power. And how is power measured as? So focal length, if focal length is in terms of meter, then power will be in terms of diopter, which is represented by the symbol capital D. So power will be equal to 100 divided by F if F is taken to be in centimeters. Is the point clear? So one diopter is either 1 by F in terms of meter or 100 by F in terms of centimeter. Right? So one last concept we'll see for the day, that is two lens in contact with each other. If two lenses are in contact with each other, what would happen? Their focal length is added or power is added? The reciprocal of focal lengths will get added. So if I take the optical centers to be O and O dash, generally when you talk about the lens, they are thin lenses. So when I take the object to be here, okay, which I'll take it as A for example, for instance. Then if this distance is U, okay, and the final image is formed at B, let's say the focal length of the first lens is f1 and the focal length of second lens is f2. See here I've taken two convex lens, not necessary it need to be, they need to be convex lens only. But applying lens formula, not lens maker's formula, lens formula for first lens, what can I say? 1 by V1 minus 1 by U is equal to 1 by F1. So this is equation 1. Similarly, applying lens formula for second lens, what will I get? 1 by V minus 1 by V1 is equal to 1 by F2. Because why did I take it? V1 will become the object distance with respect to second lens. So this will be 2. When I add 1 and 2, what will we get? 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. So 1 by V minus 1 by U will be 1 by F effective, which is equal to 1 by F1 plus 1 by F2. Okay, so this will be the relation between equivalent focal length and the individual focal lengths. So what will be the effective power? Effective power will be, so like this, you have n lens in contact with each other. You just need to add everything. And one important point to be remembered is, while solving problems, what should you do? Apply sign convention. So what is a sign convention followed with respect to lens? So if it is a convex lens, focal length is positive. If it is a concave lens, focal length is negative. You need to be careful with that point. Okay. So this is all about the concept of the refraction at spherical surface. Then what did we see? Lens maker's formula and power of lens. And last point was contact. When the lens were in contact with each other, what will happen to the focal length? Is that clear? So these are all the points. And remind me, we need to discuss about what happens to magnification. After that, we are done with the first part. Ray optics part is over. We need to go to optical instruments. Okay. And also remind me, I need to explain the lens formula. We have to see the derivation. We didn't see it yet. Okay, so tomorrow we'll see lens formula. Before that, we'll see what will happen to the magnification here. And then we'll go to the optical instruments. Right? So those are online. I hope you could understand.
Yes, sir.
Yes, sir.
So that's it for today. We'll wind up.
Thank you, sir.